And in the world of software engineering, a function is a contract. You provide a set of inputs, the logic executes, and a deterministic output emerges, provided the runtime environment does not throw an exception. The Raptor 3 can be understood through exactly this lens, but with one crucial twist: the function is not executed on silicon. It is etched into superalloy and driven by cryogenic fluids at the edge of material existence. The engine is a physical algorithm, a hardware-level execution loop, where the instructions are fluid dynamic events, the registers are high-pressure manifolds, and the clock cycle is the furious cadence of a turbopump spinning at tens of thousands of revolutions per minute. And the function signature, inputs, processing, output. Every software routine begins with a signature. For the Raptor 3, the signature is deceptively simple. In this code snippet represents a function call that calculates engine thrust based on multiple input parameters, including propellant flow rates, throttle setting, and gimbal angle. And the inputs are liquid oxygen and liquid methane, metered with a precision that would be the envy of any industrial process control system. The throttle command is a digital signal, a value between roughly 40% and 100% of rated power that arrives from the vehicle's flight computer. The vector angle is a set of gimbal coordinates that aim the entire engine assembly. The output, thrust, is a vector force measured in meganewtons, but it is also a complex waveform of pressure, temperature, and vibrational harmonics that must stay within a tightly bounded envelope. In the processing block, the function body, is where the analogy deepens. In a CPU, logic gates transform electrical states. In the Raptor 3, the logic gates are the main liquid oxygen and fuel valves, the proburner injectors, the main injector plate, and the turbine bypass ports. These are not binary on/off switches in the traditional sense. Most operate in continuously variable positions, but from a control perspective, they behave like a set of analog comparators and gain stages that modulate the flow of mass and energy. When the flight computer increments the throttle command by 1%, a cascade of events ripples through the engine. The proburner oxidizer valve opens slightly, the turbine speed increases, the pump discharge pressure rises, the main chamber injector pressure climbs, and after a finite delay, the thrust increments. This cascade is the engine's instruction pipeline, and just as in a superscalar processor, managing the hazards, data dependencies, resource conflicts, and timing skews is the central challenge of engine control. In the runtime environment, extreme and unforgiving, every programmer knows that a function can be logically flawless and still fail if the runtime environment is hostile. In a data center, you worry about thermal throttling, voltage droop, or a cosmic ray flipping a bit. In the Raptor 3, the runtime environment is a region of the combustion chamber where the temperature exceeds 3,300 degrees C. The pressure is over 350 bar, and the heat flux through the copper alloy liner can reach 100 megawatts per square meter. At these energy densities, the hardware is perpetually on the brink of phase change. The engine wall is not a static boundary. It is a dynamic participant that must be actively cooled by circulating cryogenic methane through hundreds of microscopic channels that are themselves part of the engine's plumbing logic. And in this environment, a bug is not a segmentation fault. It is a burn-through that vents high-pressure gas into a cavity not designed to hold it. An exception is not a stack trace. It is a hard start, a combustion instability event, or a turbine overspeed that liberates blades from their disk. The Raptor 3's control system therefore operates under a ruthlessly enforced design contract. There is zero tolerance for unhandled exceptions. Every conceivable fault mode must be either prevented by physical design or mitigated by a real-time control response that executes in microseconds. This is not the world of fail-fast software. It is the world of fail-never, where the system must degrade gracefully even when individual sensors report implausible data or a valve position feedback potentiometer begins to drift. And the control loop as a real-time operating system. At the heart of the digital logic is a control loop that runs at multiple kilohertz. If you were to inspect the source code running on the engine's avionics, you would find a prioritized interrupt-driven architecture. The highest priority interrupt is the combustion stability watchdog. A network of high-speed pressure transducers, mounted flush with the combustion chamber wall, samples the pressure field at rates that capture the earliest whisper of acoustic resonance. If the signal begins to exhibit a frequency peak that matches a known chamber mode, say the first tangential mode at around 2000 Hz, the control algorithm must respond within a handful of cycles. The response might be a subtle modulation of the main oxidizer valve to disrupt the standing wave, effectively dithering the flame front in a way that is conceptually similar to how a modern CPU spreads electromagnetic interference across a frequency band to pass emissions testing. And below the watchdog sits the primary control loop, which manages the engine's main operating point. The loop reads the commanded thrust, compares it with the measured thrust derived from chamber pressure and nozzle exit pressure, and calculates an error signal. This error signal is fed into a set of nested proportional integral derivative (PID) controllers that adjust the proburner valves, the main injector pressure drop, and the turbine bypass. But unlike a textbook PID implementation, the Raptor 3 controllers must account for the fact that the plant is highly nonlinear. At low thrust levels, the injector pressure drop is small, and the combustion dynamics are sensitive to small perturbations. At high thrust, the system is stiffer, but the thermal loads are enormous. The control laws incorporate gain scheduling, effectively a set of pre-computed lookup tables that switch the PID coefficients based on the current operating regime. Much like a just-in-time compiler, selects optimized code paths based on runtime profiling. And latency, the inescapable physics of throttle response in networking. Latency is the delay between a packet being sent and its acknowledgement. In rocketry, latency is the delay between a throttle command and the actual change in thrust. For the Raptor 3, this latency is on the order of tens of milliseconds, an eternity to a digital controller, but remarkably fast for a machine moving tons of cryogenic fluid. Understanding the sources of this latency is key to appreciating the engine's digital architecture. And the first component is transport delay. When the controller commands a valve to move, the actuator, a high-torque electric motor driving a ball or butterfly valve through a gear train, requires finite time to slew. Then the changed flow of oxidizer or fuel must travel from the valve, through the manifold, into the proburner, through the turbine, and finally into the main injector. This is not an instantaneous pressure wave. It is a mass flow transient that propagates at the speed of sound in the fluid, but the fluid itself is moving, and the compliance of the plumbing smears the transient. The result is a phase lag that increases with the physical distance between the valve and the combustion zone. And the second component is the thermal inertia of the engine hardware. The thrust produced by a rocket engine is not solely a function of the instantaneous propellant flow. It also depends on the temperature of the chamber walls and the injector face, which influence the rate of propellant vaporization and the boundary layer thickness. When you command a rapid throttle up, the hardware must soak in the new thermal state before the thrust fully stabilizes. This thermal time constant is analogous to the thermal time constant of a CPU core when it transitions from idle to full load. Only here the junction temperature is measured in thousands of degrees, and the cooling solution is a transpiration-cooled combustor. And SpaceX has invested heavily in minimizing control latency because the Starship architecture demands it. During the propulsive landing maneuver, the now iconic flip and burn that transitions a falling Starship from horizontal freefall to vertical touchdown, the engines must throttle deeply and respond to rapid changes in vehicle attitude. A latency of even 50 milliseconds can translate into a meter of altitude error, which at zero altitude is the difference between a successful catch by the launch tower and a high-velocity disassembly. By integrating sensors directly into the 3D printed engine components and co-locating the control electronics on the engine itself, SpaceX has shrunk the signal path from sensor to actuator to the absolute physical minimum, effectively turning the engine into a distributed embedded system where each major subassembly hosts its own local intelligence. And combustion instability as a race condition to a computer scientist, the most terrifying class of bugs is the race condition. Two concurrent processes accessing a shared resource without proper synchronization, leading to non-deterministic, catastrophic failure. Combustion instability is the thermodynamic equivalent. The combustion chamber is a shared resource where the fuel injection process and the heat release process must remain tightly coupled. If a pressure wave in the chamber momentarily reduces the local injector pressure drop, the flow of propellant into that region can slow or even reverse, causing the local heat release to dip. That dip reinforces the pressure wave, which travels to the injector face again, creating a positive feedback loop that can grow exponentially. And the Raptor 3 solution to this race condition is a combination of hardware synchronization and software locking. On the hardware side, the injector elements are designed with a high pressure drop, typically 15 to 20% of chamber pressure, so that small chamber pressure oscillations do not significantly modulate the injection rate. This is analogous to using a mutex that ensures only one process can alter the shared variable at a time. On the software side, the combustion stability watchdog we mentioned earlier acts as a dynamic lock. It detects the buildup of coherent oscillations and actively modulates the valves to break the coherence, essentially injecting noise into the feedback path to prevent the oscillation from locking onto a resonant mode. This technique, known as active combustion control, is rarely implemented in operational engines because of the extreme bandwidth required. The Raptor 3 is one of the first production engines to attempt it at scale, and it does so by treating the combustion chamber as a high-speed signal processor. And abstraction layers, from fluid physics to mission software. One of the most elegant aspects of the Raptor 3 digital logic is the abstraction hierarchy that separates the raw physics from the mission-level software. At the lowest layer, you have the physical plant, the turbomachinery, the injectors, the chamber, and the nozzle. This layer is governed by the Navier-Stokes equations, chemical kinetics, and heat transfer, a set of partial differential equations so complex that even the most powerful supercomputers cannot solve them in real time. And the next layer is the engine control unit, ECU, a hardened embedded computer that runs a real-time operating system. The ECU does not attempt to solve the full physics. Instead, it uses a reduced order model, a set of differential equations that capture the dominant dynamics of the engine with a fraction of the computational cost. This model is continuously updated with sensor data and provides the ECU with estimates of unmeasured quantities, such as the turbine inlet temperature or the combustion chamber heat flux. In software terms, this is the device driver layer. It translates high-level commands into low-level actuator signals while hiding the messy details of the hardware. And above the ECU sits the vehicle-level flight computer, which issues throttle and gimbal commands based on the mission phase. The flight computer does not need to know the proburner mixture ratio or the pump shaft speed. It simply requests a thrust vector and trusts the ECU to deliver it. This separation of concerns is identical to the way a user mode application calls a kernel API without needing to know the specifics of the memory management unit or the disk controller. It allows the engine team to iterate on the control algorithms independently of the guidance, navigation, and control (G&C) team, as long as the interface contract, the thrust response envelope, is maintained. And the Raptor 3 as the most digital engine yet. What elevates the Raptor 3 beyond its predecessors is the degree to which this digital logic has been embedded directly into the hardware. In a conventional rocket engine, sensors are bolted on as afterthoughts, a pressure transducer here, a thermocouple there, each with its own wiring harness and connector. These harnesses are heavy, they vibrate, they chafe, and they are a prime source of in-flight anomalies. The Raptor 3 takes a radically different approach. By leveraging advanced additive manufacturing, SpaceX has integrated sensor ports, signal conduits, and even strain gauges directly into the structure of the engine. The main combustion chamber is 3D printed with internal channels that serve double duty. They carry cooling fluid, but they also house embedded fiber optic temperature sensors that provide a continuous thermal map of the chamber wall with millimeter spatial resolution. And this integration collapses what was once a sprawling network of discrete components into a unified electromechanical system. The number of external wires on a Raptor 3 is a fraction of that on an engine of comparable power from a previous generation. This is not merely a manufacturing convenience. It is a deliberate strategy to minimize points of failure. Every connector that is eliminated is a potential open circuit that cannot occur. Every sensor that is printed into the metal is a static analysis check that the engine passes by construction, because the sensor cannot be miswired or installed backward. In the language of software engineering, SpaceX has refactored the engine's hardware to reduce its cyclomatic complexity, making the system more predictable and easier to verify. And this philosophy of digital integration extends to the engine's startup and shutdown sequences, which are among the most hazardous phases of operation. In the Raptor 3, the startup is a choreographed sequence of valve openings, igniter firings, and spin-up commands that must occur with split-second timing. If the methane reaches the proburner before the oxygen, or if the igniter fires too late, the result can be a hard start that destroys the engine. The control software executes these sequences as a deterministic state machine, with explicit transition guards that check sensor readings before advancing to the next step. This is the same pattern used in safety-critical software for medical devices or nuclear reactors, where a missed state transition can have irreversible consequences. And the engine as a data generator. Finally, it is worth recognizing that the Raptor 3 is not just a consumer of digital commands. It is a prolific producer of data. During a single 6-minute static fire, the engine sensor suite generates gigabytes of time series data, pressures, temperatures, flow rates, accelerations, acoustic spectra, and valve positions. This data is the raw material for a continuous improvement cycle that is central to SpaceX's development philosophy. After every test, the data is fed into a ground-based analytics pipeline that compares the observed behavior against the predictions of high-fidelity computational fluid dynamics models. Any discrepancy, a temperature that rose faster than expected, a vibration mode that appeared at an unexpected frequency, triggers a root cause investigation. And over hundreds of tests, this feedback loop has allowed SpaceX to refine the engine's control laws and even its physical geometry. In a very real sense, the Raptor 3 is a learning system. The engine that flies on a given Starship mission has been trained on the cumulative experience of the entire test campaign, much as a machine learning model improves with more data. This data-centric approach is what enables the rapid iteration that traditional aerospace companies find so difficult to replicate. It is the ultimate expression of the digital logic of propulsion. The engine is not a static artifact, but a continuously evolving software-defined machine. And transition to the propellant menu. All of this digital sophistication, the kilohertz control loops, the embedded sensors, the fault-tolerant state machines operates on a physical substrate whose fundamental characteristics are determined by the choice of propellant. The chemical properties of the fuel and oxidizer define the instruction set of the engine, the energy available per clock cycle, the thermal constraints, the coking behavior that determines reusability, and the density that drives tank size. Before we can fully appreciate the Raptor 3 control architecture, we must first understand why SpaceX chose methane over its rivals. The next section, 2.1, the propellant menu, kerosene vs. hydrogen vs. methane, will examine this foundational architectural decision, comparing the three primary propellant options as one might compare programming languages, each with its own syntax, performance characteristics, and ecosystem of challenges.